This is an objective with one or more than one correct answer. By reading the following statements, we need to find out the incorrect statements among them. So to answer this, first let me start with option C, because here I need to explain the meaning of the D and L forms. So I'm talking about option C. Here actually the D and L forms, they do not refer to the sign of optical rotation. Here they do not refer to the sign of optical rotation. It means they are not indicating whether the given compound is dextro or levo. Remember, in the case of dextro we use the symbol D or the plus sign. In the case of levo we use the symbol L or the negative sign. And it is small alphabet D and alphabet L, but not the capital D and capital L. Then what is this capital D and capital L indicates? So this D and L, they refer to the configuration of stereoisomer relative to that of glyceraldehyde. So D and L indicates the relative configuration with reference to glyceraldehyde. And what is glyceraldehyde? This is the structure of glyceraldehyde. In this one, this is the chiral carbon. So on this chiral carbon, whenever the OH group is on the right hand side, this is called as the D-glyceraldehyde. And if the OH group is on the left hand side, like this is called as L-glyceraldehyde. So any other compound in which the OH group on the most distant chiral carbon is on the right hand side, that is called as, that comes under D configuration, and if it's on the left hand side, that comes under the L configuration. So here the D enantiomer rotates the plane polarized light to the right and L enantiomer to the left. This statement is wrong, isn't it? Because the terms D and L do not refer to the sign of the optical rotation. It just indicates the relative configuration with reference to glyceraldehyde. So definitely this is a wrong statement. That's what we want. It should be in our answer. Then come to option A. D and L forms are enantiomers. And this is true only for a compound which is having one chiral carbon. Isn't it? If we take the case of the same glyceraldehyde, whose structure is like this. So as there is a chiral carbon, definitely it rotates the plane polarized light either towards the right side or left side. And suppose if this is the dextrorotatory in nature, this particular structure which is the L form, definitely this will be levorotatory in nature. So the D and L forms are enantiomers only whenever there is one chiral carbon, but that is not for a compound with more than one carbon atom, which is chiral. For example, if we take this particular compound, as informed, this comes under the D configuration. This is the chiral carbon, and on the distant chiral carbon, the OH group is on the right hand side. So definitely this comes under the D configuration. So by looking into the structure, we cannot say whether this is a dextro form or levo form, because that is nowhere related to the presence of OH group on the right hand side, isn't it? So D and L forms are enantiomers. This is again a wrong statement. So our answer should be even option A. Then come to option B. A chiral compound can have chiral centers. For example, let me take the case of meso compound, that is mesotartaric acid, and its structure is like this. So now here this mesotartaric acid has two chiral centers, but because of the presence of plane of symmetry, what is the meaning of plane of symmetry? The plane which divides the molecule into two equal and identical halves, that is called as plane of symmetry. So because of the presence of the plane of symmetry, its optical activity is 0. So this is an achiral compound, but still it can have chiral centers. So this is a correct statement. as this is a correct statement, definitely this cannot be in our answer. So let's move to the last one. An optically inactive substance must be achiral. For example, what is racemic mixture? It is nothing but the equimolar mixture of both dextroform and levoform, as both are present in equal concentration. So the net optical activity of this particular mixture is equal to 0. So even though the individual forms, the individual molecules are having chiral centers, as both the molecules are present in equimolar concentration, the net optical activity is 0. So an optically inactive substance must be achiral. This is again a wrong statement, because they are chiral compounds, but because both are present in equimolar concentration, the net optical activity is 0, or it is becoming optically inactive. That is the reason why our answer should contain even option D. So correct answers are option A, option C, as well as option D.